Intersection of two planes. So again, we got to figure out if they are case 1, 2, or 3, if they intersect parallel or coincident lines. Now, I've obviously written the title, so we know what's going to happen, but I do need to disprove the other two before we go anywhere. If we take a look at plane number 1, the normal to the first plane is 1 and negative 1, 1. And the normal to the second plane is 2, 2, negative 2. Quickly, by looking at this, I'll look at my z values. I have to multiply by negative 2 in order to do that. And I know if I multiply my x values by negative 2, I do not get the same term. Okay? So these normals are not parallel to each other, or they're not representing the same direction. So if the normals don't represent the same direction, that means these are not going in the same direction. So we know they are not parallel and they are not coincident. So from here, what we're going to have to do is we're going to use our elimination again to go through this. Now remember, the intersection of two planes creates a line. Okay? And I'll quickly draw this out one more time. So if we have two planes here, here's one of them. Here's the other. When they intersect each other, it's going to make a line. Okay? This is very important because this is very different from what we were looking at before. We are going to need parameters to this line. So the first thing we're going to do is we're going to eliminate our x's. Just like we've been doing previously. We eliminate our x's. I'm going to multiply the first equation by negative 2. And that's going to give me equation 1 again, but negative 2x plus 2y minus 2z is equal to negative 6. Equation 2 will be the same as before. 2x plus 2y minus 2z is equal to 3. We're going to add these two together. This will give us 0x plus 4y minus 4z is equal to negative 3. So our equation number 3 can read 4y minus 4z is equal to negative 3. So we have our third equation here. Now, remember, we have two equations, three variables. We can't find specific values. And that's okay because we're not looking for specific values. We're looking for a line. What we're going to do here is in a line, if you guys remember vector or parametric form, in vector form of a line, we have x naught, y naught, z naught, plus a scalar, okay, s, of direction, or t, sorry, of direction vector A, A1, A2, A3. Okay. Or in parametric form, that's written as x is equal to x naught plus TA, y is equal to y naught plus TA2, and z is equal to z naught plus TA3. This becomes important because when we're looking for an equation of a line, we need a variable or a parameter in there. We need this t. Okay. You can call it any letter you like. So what we're going to do in this question here is we're going to set one of the variables, or x, y, or z, equal to t. We're going to make it the parameter. Okay? So what we'll do in this case is we're going to set z equal to t. So z will equal our t, or our parameter in this question. So we take equation 3, and we're left with 4y minus 4t is equal to negative 3. We're then going to solve for our y. So we get 4y is equal to negative 3 plus 4t. Y is equal to negative 3 over 4 plus t. Well, that is the parametric form right there of part of the equation. That tells us the y value of the parametric form. Remember, y was equal to some number. With that, well, here we have y is equal to some number and our parameter. We've already solved part of it. We're then going to use some substitution here. We're going to substitute this y value back into equation 1, or, sorry. We're going to substitute this y value back into our equation 1 along with, where is it? There it is. Equation 1 along with our z value. Does anyone know what our z value is in this case? We've actually already solved that also. What do you mean it's the same thing? Y is equal to, that's the parametric form. What's the parametric form of z? What is it? Close, not 1, but 1t, right? We said that at the very beginning. So I've actually already solved the z form of this also. So our z form is z is equal to t, okay? So our z naught in this case is 0, and our t value is 1 again, okay? Our number in front is v, or sorry, our a3 value. So we've got those two there. We have a y, we have a z. We need to solve for the x form of this. So like we were saying before, I'm going to plug this all back into equation 1. Equation 1 said x minus y plus z is 3, I think. Yep. X minus y plus z is equal to 3. Well, I have a y and a z value. So x is equal, x minus negative 3 over 4 plus t plus z is t is equal to 3. Now I'm left with just an x variable and a t. I'm going to set x equal to some form of t. So x plus 3 over 4 minus t plus t is equal to 3. Our t's are going to cancel out. We're left with x is equal to 3 minus 3 over 4. X equals, that becomes 12 over 4 minus 3 is 9 over 4. So my x value is equal to 9 over 4. Well, what does that mean? What is my t value? Or sorry, what is my a1 value, my directional vector? Let's try to put this into vector form so we know what they're asking, or what they've given us. Well, our vector form from our parametric form, remember, vector r is equal to r naught. So what is the r naught here for the x value? Or x naught, I should say. Anyone know what the value is? 9 over 4. That's our coordinate value. What's our y naught value? Negative 3 over 4. And our z naught value? 0. There's nothing there in the z. Okay. Plus, now we're going to factor t out. I don't know if we have enough room. I'm going to move this down a little. There you go. We'll do the other two first, and then we'll make sense. What's our t value of y? 1. T value of z? T value of x? 0. There's our vector form of that equation. We only needed to put it in parametric form, but I wanted to show you guys the connection between that, because I know they all didn't look like full equations. Z was equal to t. Okay, well that just meant the point was at 0, and our direction vector was 1. And we actually found a value for x, x being 9 over 4.